Namaste students and welcome to our class. So, today we are going to tackle a very important topic from Unit 4, Moving Charges and Magnetism. We're looking at the magnetic field on the axis of a circular current loop. Now I know, derivations can seem a little bit scary, but trust me, by the end of this session, this whole idea is going to be absolutely crystal clear and you'll be 100% ready for your exams.
Okay, so to get started, let's think about a simple question. How can a plain old ring of wire, just a loop, suddenly start acting like a powerful magnet? I mean, it doesn't look like a magnet, right? But the moment you pass a current through it, it behaves exactly like one. How is that even possible? Well, have a look at this. This picture shows us exactly what's happening. The moment the current starts to flow, this loop creates an invisible field of force all around it, a magnetic field. And you can see, it has a proper north pole and a south pole, just like any bar magnet you've ever seen. So our job today is to figure out the exact strength of this field at any point along its central line, its axis. Now, to uncover this secret power of the loop, we don't need to learn a whole bunch of complicated new rules. No. We only need just one single fundamental law that explains this entire thing. And here it is, the Biot-Savart law. This, my friends, is our master tool. Now, don't get scared by all the symbols. It's actually very simple. All this equation is telling us is that any tiny little piece of a wire carrying a current, which we call dl, creates its own tiny little magnetic field dB at some point in space. That's it. That mu0 thingy is just a constant, nothing to worry about.
To make this even simpler, let's use a little story. Just imagine that our circular loop is like a big circular stadium, and standing all along the edge of the stadium is a whole team of archers. Now, each archer is like a tiny current element, a dl. And what are they doing? They are all shooting arrows, magnetic field arrows, we'll call them dB. And they're all aiming at the exact same target, a point P on the axis. Our mission is just to find out the total effect of all these arrows put together.
All right, now for the fun part, a bit of detective work. We are going to use the exact diagram from your NCRT textbook and some very simple logic. The most powerful tool we have here is something called symmetry. Let's see how it helps us solve this case, step by step. So, first things first, let's not worry about the whole team of archers just yet. Let's just pick one single current element, dl, sitting right at the top of the loop. You can see it shoots its magnetic field arrow dB towards our target, point P. Now, notice the direction of this dB vector. It's at an angle, Now, because this dB vector is at an angle, we can, break it down into two parts, into its components. One part is pointing straight ahead along the axis. We'll call this one dBx. And the other part is pointing sideways, perpendicular to the axis. We'll call that one dB perpendicular. Simple enough, right?
And here it comes. This is the big aha moment. Look at the archer at the top. His sideways component, dB perpendicular, is pointing kind of downwards. Now let's look at another archer, one standing exactly opposite him at the very bottom of the loop. Look at his sideways component. It's pointing upwards. They are in perfectly opposite directions. You see what's happening? For every archer on the loop, there is another archer exactly opposite who shoots a sideways arrow that perfectly cancels the first one out. One pushes left, the other pushes right. One pushes up, the other pushes down. And because the loop is a perfect circle, this happens for every single point. All those sideways components, all the dB perpendicular, they just cancel each other out. Poof, gone.
And this is the key idea taken straight from your textbook. The only part of the magnetic field that actually survives this cancellation fest is the forward-pointing part, the component along the axis. So our job just became so much easier. To find the total magnetic field, all we have to do is add up all these forward components, all the dBx's, from every single archer on the team.
So, after all that logical detective work, after seeing how all the sideways parts disappear, we are ready for the grand reveal, the final formula that you'll need for all your problems and exams.
And here it is, equation 4.11 from your NCERT book. This formula gives you the total magnetic field, B, at a distance x along the axis of a circular loop. The loop has a radius r and is carrying a current I. This whole expression, it's simply the result of adding up all those forward-pointing dBx components we just talked about. Let's just quickly break this formula down so it's really easy to remember. Look at the top part, the numerator. It tells you what makes the field stronger. More current, I, stronger field. A bigger loop with a larger radius r, stronger field. Now look at the bottom,
The denominator. It tells you that as you move farther away from the loop as x gets bigger, the field gets weaker. And it gets weaker quite fast. Make sense now?
Okay, now for a very, very important special case. This is a favorite question in exams, so listen carefully. What happens to the field if we are not at some distance x, but right at the very center of the loop? What happens when x is equal to 0?
Well, if you put x equals 0 into our big formula, the math simplifies beautifully. And you get this nice, small expression, b equals mu0 times I, all divided by 2r. This is equation 4.12 in your book, and it tells you the magnetic field right at the center, which, by the way, is the point where the field is the strongest. Very good. So we now have the formula for the value, the magnitude of the field. But in an exam, that's only half the story. Let's talk about some common traps, some silent killers that can make you lose marks, especially when it comes to finding the direction. So here's a very common point of confusion for many students. We know there are a couple of different right-hand rules in this chapter, don't we? So which is the correct one to use to find the direction of the magnetic field for a circular loop? If you use the wrong one, you could lose marks for sure.
Okay, this slide is super important, so please pay close attention. For a circular loop, you take your right hand and you curl your fingers in the direction the current is flowing. Your thumb will then automatically point in the direction of the magnetic field along the axis. This is different from the rule for a straight wire, where your thumb points with the current. Please, I'm telling you, make a special note of this difference. It's even highlighted in a footnote in your NCRT book. Don't mix them up.
Fantastic work. Now that we've really mastered the circular loop, let's just zoom out for a second and see how this one idea connects to the bigger picture. And then we'll do a quick summary of everything we've learned.
So you might be thinking, sir, why did we spend so much time on just one little loop of wire? Well, because this simple current loop is like the basic atom, the fundamental building block for much bigger and more powerful devices. When you take hundreds of these loops and stack them together, what do you get? You get a solenoid. And a solenoid is the heart of every single electromagnet you'll ever see.
All right, so for a quick revision, just before your exam, here are the main points to remember. First, a circular current loop is a magnet. Second, we find its field using the biotes of art law and the magic of symmetry. Third, the perpendicular parts of the field cancel out, and only the parts along the axis add up. Fourth, we find the direction using the special right-hand rule for loops. And finally, the big formula for the field on the axis. Got it?
And I'll leave you with one final question to think about. We've just proved that moving charges, a current in a loop, create a magnetic field. In fact, a great scientist named Ampere suggested that all magnetism, everywhere, comes from tiny circulating currents. So my question to you is, what tiny currents could possibly be flowing inside a simple, solid, permanent bar magnet to give it its magnetic field? Think about it. The answer is hiding inside the atoms themselves.